imagine teaching robots to move kind of like choreographing a dance. But here's the catch. Robots usually need a ton of instructions, which makes things slow and clunky. That's where FAST, short for fast action stemming, comes in. It's got this clever trick called the discrete cosine transform. Yeah, fancy name. But think of it like compressing a song into an MP3. Smaller, faster, but still clear. So now robots can learn tricky stuff like folding laundry or packing groceries way more efficiently. Plus, FAST works with all kinds of robots without needing extra tweaks. Just imagine telling a robot, "Hey, fold that shirt," and boom, it nails it, smooth and quick. And the best part? It cuts training time by up to 5 times. All right, let's jump in and see how this magic works.
Let's start by looking at why tokenizing robot actions even matters. Large transformer models do really well at learning robotic behaviors, but they need a good way to turn continuous actions into discrete tokens. Traditional approaches often just split each dimension of the action space into bins at every time step. The problem? At high speeds, actions become so similar from one moment to the next that the model struggles to learn meaningful differences. Here's where FAST, short for fast action stemming, comes in. It compresses action data before feeding it to the vision language action model. How does it do this? By using the discrete cosine transform, or DCT. DCT, which is also used in JPEG image compression, takes continuous signals and breaks them down into components that capture slow and fast changes. This reduces redundancy in high-frequency data, helping the model learn faster and handle complex actions more effectively. Check out Figure 1 for a side-by-side comparison of FAST versus a standard tokenization approach. The chart shows how quickly each method reaches top performance. FAST hits peak performance about 5 times faster. The images next to the chart show 2 kinds of tasks. One where the robot performs fine manipulations like folding or grabbing, and another where it navigates changing environments. FAST manages both with fewer hiccups. So the main takeaway here is, FAST tackles the weaknesses of binning methods by compressing repetitive, high-frequency actions. As a result, training is faster, performance is better, and robots handle tricky tasks more reliably. Moving on, let's dig deeper into the core principle behind FAST. In many robot tasks involving quick, precise motions, each action looks almost identical to the previous one. If we just break data into small chunks, like in basic binning, models can end up merely copying the last action. This doesn't help them learn the underlying patterns. FAST fixes this by compressing data first with DCT. Picture it like JPEG for robot actions. DCT finds the essential frequencies in the data. Slower changes get captured in the low frequencies, and sudden movements in the high frequencies. By compressing the data this way, we reduce the repetition that plagues high-frequency control. Check out Figure 2. It illustrates how FAST turns raw, high-frequency robot data into compressed tokens. On the right, there's a chart comparing performance of DCT-based tokenization against a basic binning approach. As control frequency climbs, the gap in performance gets bigger, and FAST clearly outshines the old method. So the lesson here is pretty straightforward. Compressing first makes it way easier for the model to handle rapid, detailed movements. Next, let's talk about why FAST pulls ahead of other tokenization strategies. Older methods, whether they're simple binning or vector quantized autoencoders, can get tripped up when consecutive actions barely change. This leads to action copying, where the model just repeats what it just did, giving you little real predictive power. Now consider the problem the paper is trying to solve. Training policies that predict a sequence of future robot actions. Traditional binning divides each action dimension into discrete bins at every time step. This generates a massive number of tokens at high frequencies, bloating the model's input and making predictions noisy. Enter FAST, once again leveraging DCT. Instead of 1 token per dimension per time step, DCT compresses repeated or predictable patterns. That means fewer tokens and better predictive accuracy. Look at Figure 3. In the top chart, as you increase how quickly data is sampled, the prediction error of the naive method shoots up, while DCT-based FAST stays comparatively low. In the smaller charts, you can see how FAST's predictions track the ground truth more closely over time, especially when the robot moves quickly. The bottom line? Compress first, tokenize second. That helps the model forecast robot actions more accurately and more efficiently, even in high-speed scenarios. Continuing on, let's unpack how FAST uses the DCT for compressing high-frequency robot data. The core issue is that fast robot movements often produce redundant signals. Each action is nearly the same as the last. That's not a lot of fresh information for the model to learn from. DCT solves this by translating the time domain signal into frequencies. Lower frequencies encapsulate broad, gradual changes. Higher frequencies capture abrupt shifts. Because most robotic tasks don't need every little high-frequency fluctuation, DCT can trim down the redundant parts without losing the important details. It's also quick and easy to implement, just like what happens with image compression in JPEG. FAST applies DCT to each action dimension individually. Pertsch. It starts by normalizing the data to a certain range. Then it performs DCT, extracts the frequencies, and applies a threshold to drop tiny components that don't add much value. There's a scaling factor you can tune if you want more or less compression. Fewer tokens mean faster training, but you don't want to sacrifice too much accuracy. In short, DCT is the reason FAST feels fast. It dramatically shrinks the amount of data that the model needs to process. This efficient compression is especially handy when tasks involve quick and complex robotic movements. Now let's go step by step through FAST's tokenization pipeline. Imagine you have a window of robot actions. First, everything gets normalized, so each dimension fits neatly into a fixed range. This way, the transformation works uniformly across different scenarios. Next, you apply the DCT to each dimension. This breaks the signals down into those frequency components we just talked about. Then comes quantization, where the continuous DCT coefficients get rounded off so they take up fewer bits. After that, you flatten out the coefficients into one long vector, placing the low-frequency components first because they capture the bulk of the motion. Finally, you apply byte pair encoding, or BPE. Originally a text compression technique, BPE merges frequently repeated elements into a single token. Here, that means any repetitive patterns in the action data get consolidated. Check out Figure 5 to see a visual walkthrough of this pipeline. The pseudocode also lays out the process. Compute DCT, quantize, flatten, and then compress with BPE. This chain is fully reversible, so you can reconstruct the original sequence if you need to. The end result is a concise set of tokens that efficiently represent the robot's high-frequency actions. Next, let's see how FAST performs in real-world tasks and how you can easily try it out yourself. The paper introduces the idea of a universal action tokenizer. Instead of having a tokenizer trained on just one robot or one specific dataset, they train FAST on over 1 million short action sequences collected from multiple robots. They call this version FAST Plus. It's designed to work right out of the box for different robot setups without extra fine-tuning. Want to use it? The snippet of code in this section shows how you can load the pre-trained tokenizer with just a few lines using Hugging Face's autoprocessor. It's as simple as importing the library, loading the model, and feeding it your action data. If you need something more specialized, there's also a script for training a custom tokenizer. To test FAST in diverse scenarios, the paper looks at tasks like folding laundry, grabbing toast, clearing a table, and packing groceries. Each one tests different skills. Some need speed, others precision. Check out the figure here, which shows 6 example tasks set to an arrow. They also use the Libero benchmark, a set of simulated manipulation tasks, to measure average performance. The upshot? FAST holds up well in both simulation and real-world tasks, demonstrating its versatility across multiple robot control problems. Let's talk about token counts and why they matter. If your tokenizer churns out too many tokens, the model has a lot of data to process, slowing down training, so compression is a big win when done right. Check out Table 1. It shows the average number of tokens per action chunk for 4 different datasets. A naive approach, 1 token per action dimension per time step, can generate hundreds of tokens. Take the shirt folding dataset, for instance. The naive method comes in at 700 tokens per chunk. FAST slashes that to 53 tokens, giving you about a 13x reduction. Even on slower tasks, FAST usually cuts the token count nearly in half. Why is that important? Fewer tokens mean the model can spend its effort on learning rather than churning through noise. Sure, there's some loss because of compression, but the experiments show that the default settings strike a good balance between saving tokens and keeping important details. The key message here is that FAST's compression dramatically reduces training overhead while preserving essential action information. Now let's compare FAST's performance to other tokenizers and check how well it generalizes. Look at Figure 6. It shows how FAST and its universal variant, FAST Plus, stack up against naive tokenization on 4 tasks. FAST crushes it in high-frequency tasks like table bussing and t-shirt folding, delivering higher success rates and better progress scores. Moving on to Figure 7, we see how a DROID-trained policy using FAST generalizes across different university labs, all with 0 extra training. The robot can pick up items, open drawers, and turn faucets using natural language prompts in unseen environments at Berkeley, Stanford, and the University of Washington. That's a strong testament to FAST's robustness. Then, check out Figure 8. It compares compression ratios for FAST+ on various robot datasets. Whether it's single-arm tasks, bimanual actions, dexterous hands, or humanoids, you still get solid compression. Fewer tokens, but without losing critical motion details. In other words, FAST isn't just good. It's good everywhere it's tested, adapting well to different tasks and setups. Ever wonder if FAST is tied to a particular model architecture? This section answers that question. They trained OpenVLA, a well-known sequence model, using FAST on the t-shirt folding task. Check out the results. Compared to OpenVLA's original tokenization, FAST delivered a noticeable boost in performance. That's a clear sign. FAST plays well with others. But what about byte pair encoding? How big a difference does that make? They dropped BPE in some experiments to see what happens. On tasks like table bussing and t-shirt folding, performance got worse without it. Why? DCT often outputs many zero coefficients, which become repeated tokens that don't carry extra information. BPE merges those repeated elements, reducing token load and speeding up inference. Lastly, look at Figure 9. It pits FAST against Pi0, a diffusion model. On smaller datasets, like Libero and t-shirt folding, both do similarly well. But on bigger ones, like table bussing, FAST trains faster and reaches higher performance. In the DROID environment, FAST follows language prompts more closely. P0 does have one advantage, though it can predict whole action chunks at once, making inference faster. And ORNI. FAST decodes actions token by token, which can slow things down. It's a trade-off the researchers plan to explore further. But for now, FAST seems like the more reliable choice for complex tasks. Let's see. FAST in action for long horizon tasks. Look at Figure 10 for a robot folding laundry using P0 FAST, which combines a diffusion model, P0, with FAST's compression. The images show each step of the folding sequence. Previously, this was too complicated for other tokenizers to handle effectively. Now the robot completes it successfully. Then, glance at Figure 11. It compares P0 FAST to a top-of-the-line diffusion model on 5 tasks. Pi0 FAST either matches or beats the diffusion model's success rates, including the challenging laundry folding scenario, and it does this with around 5 times fewer GPU hours during training. That kind of efficiency is critical when training at scale. They also tested P0 FAST on a massive dataset with over 900 million timesteps, including public datasets like DROID and Bridge v2. Despite this huge variety, performance remained strong. This tells us FAST can handle industrial-scale robot learning without melting your hardware budget. Finally, we come to the future outlook for FAST. For now, it's been tested on what you might call stationary robot setups. Arms, hands, etc. What about mobile robots, or more complex morphologies like humanoids? That's one direction they're excited to explore. They also suggest experimenting with alternative compression methods, or non-autoregressive decoding, to speed up inference, which is currently slower than diffusion models, since FAST decodes tokens one by one. They point out that vision language action models in general need to juggle 3 big goals: train quickly, understand language well, and control robots precisely. Future research might focus on balancing these elements more effectively and making the models even more adaptive to new tasks or settings. Inference speed remains a challenge. FAST outperforms many methods in accuracy, but if we want real-time control for more complex tasks, faster decoding will be key. Borrowing tricks from large language models, like quantization and specialized inference kernels, might be the way forward. Overall, FAST's compression-based approach has proven effective and opens the door to more efficient, scalable robot training. Yet there's clearly a lot more to explore, especially in larger and more varied environments. Thanks for joining us today. Happy learning and stretching together.